Okay. In this tutorial we're looking at section 6.6, which is maximum and minimum problems. Okay, so for maximum and minimum problems, in many practical situations it's necessary to find the maximum or minimum value of the function that describes it. For example, if you're running your own business, you'd always want to minimize the production costs while maximizing the profits. Okay, so these are pretty typical questions, and then to maximize offer things like volumes as well, or areas or perimeters, things like that. Okay, so we've just got some things to make sure that you do. Okay, which is draw a diagram. Okay, so make sure you draw a picture. If there's more than one variable, find a link between the variables. Okay, so you need to find a link between some variables. Find an equation for the quantity to be maximized or minimized. Okay, we're going to differentiate the expression, equate it to 0, and solve for the unknown variable. We need to reject any unrealistic solutions. Often our negative values are going to be unrealistic because it might be a negative volume or area or time, something like that. Okay, check the nature of the stationary points, so see if they're maximum or minimum. Okay, find the endpoints. Okay, and I'll just say, check the nature of the stationary points. Well, if you've only got one that you can use and you're asked to maximize something, well, you know it's going to be a maximum, and then you're wasting your time actually checking to see what it is. So make sure you actually use your noggin a bit there. Okay, find the endpoints. Okay, compare the endpoints to the maximum and minimum values. Just because there is a stationary point doesn't mean that that's actually going to be our maximum or our minimum value. It could just be one of our endpoints. Okay, draw a rough sketch to double check solutions. So sometimes it's good to sketch a little graph, something like that. And make sure you answer the actual question, okay, and make sure you include units. All these questions are most likely going to include units. Okay, so we should have a sentence at the end. Okay, so we'll have a look at a worked example. Okay, I think we've got two worked examples to do. Okay, so we have the new owner of an apartment wants to install a window in the shape of a rectangle surmounted by a semicircle in order to allow more light into the apartment. The owner has 336 centimetres of wood for a frame to surround the window. They want to determine the dimensions of the window that will allow as much light into the apartment as possible. Okay, show you that the area in centimetres squared of the window is A equals, we'll get to this bit, sorry, I'll just draw our picture first that we're told. Okay, so we have a rectangle here. And we're saying that is 2x, this is h, and then we have a semicircle up here. Okay, and this line here we don't actually have to include. Okay, and we know we've got 336 centimetres of wood. Okay, and we want to show that the area, okay, A equals 336x minus a half times 4 plus pi times x squared. Okay, so what we are looking at, okay, is we need to find our area. So our area of a rectangle, I'll say AR, well that's going to be 2x times h. So 2xh. Okay, area of our semicircle, I'll just say AFC. Okay, well, and we know our area of a circle is pi r squared. Okay, well, our radius is going to be half of this, so it's going to be x. Okay, so it's pi x squared, and we know we only actually need half of it. Okay, so the total area of our window is going to equal our 2xh, okay, plus a half pi x squared. Okay, so we're not finished yet. Okay, because we're clearly not where we should be, and the problem is we've got that h. Okay, so we know that the perimeter of our window, okay, has to equal 336. Oops, sorry, too many threes there. 336. Okay, we know the perimeter of a semicircle. So perimeter of our circle, okay, is usually pi times our diameter, so it'd be pi times 2x, okay, but we only want half of it. So we can really say that we've just got pi x. Okay, then we also need perimeter of our rectangle part. Well, that's going to be our h and another h, so 2h and 2x. Okay, so we know all up, when we put all this stuff together, that we're going to be 336 equals 2h plus 2x plus pi x. Okay, and what we want to do is rearrange for h. So we want to get rid of our h in our area equation with an x. Okay, so when we do that, we get, well, 2h is equal to 336 minus 2x minus pi x. Okay, so h is going to equal then a half outside of 336 minus 2x minus pi, so pi x. Okay, so now that we've got that, we can put our h in for our equation up here. Okay, so I'm just going to come up here now for our work. So say, well, we had our area equals 2x times our h value, which is now a half times our 336, take 2x, take pi x, okay, plus a half times pi x squared. Okay, so what's good with some of this is we can do a bit of work on here. Okay, so just making sure I've got this right. Yep, so our half and our 2 is going to cancel out. Okay, so we're left with x outside of our 336 minus 2x minus pi x plus a half pi x squared. Okay, so we're getting there. So what we'll do is we'll multiply out by our x, and so we've got 336x minus 2x squared minus pi x squared plus a half pi x squared. Okay, so we're getting there because we can say now that we've got 336x and take away 2 plus a half pi x squared. Okay, which we can simplify that by taking we can take this half out. So we've got 336x minus a half outside of 4 plus pi x squared. Okay, as required. That's what we needed in the first place. So you see there's a fair bit of work there to get there, but we had this problem with h, so we knew we wanted to maximise our area, but we also knew that we had our 336 centimetres of wood for our perimeter. Okay, so using that link we could get rid of that variable h that we didn't want. Okay, so we want to hence determine to the nearest centimetre the width and height of the window for as much for which the area is the greatest. Okay, so what we need to do is we need to take our derivative of this. So we're going to go dA dx. Okay, well, x is going to drop out on this one. Okay, and then our 2 is going to come out the front to get rid of that, and so we'll have 4 plus pi x. Okay, we want to find when that's equal to 0. That's 4 plus pi times x. Okay, so what we do is we take away our 336 minus our 4 plus pi x. So we'll get 336 on 4 plus pi equaling x. Okay, so that means that x equals 47.05 centimetres. Okay, so I'm not going to worry about checking that because we know that we're maximising it. We've only got one value there, so there shouldn't be anything else that we need to worry about. Okay, so our maximum area is going to be this height, but we also need our h value as well. So we've got to work out our h value. I might switch colours for this. Okay, so we can say h is equal to a half outside of 336 minus 2 times 47.05 minus pi times our 47.05. Okay, and that gives a h value also of 47.05 as it works out centimetres. Okay, so we've finished that worked example. Okay, so we've got one last worked example that we're going to have a look at. Okay, which is find the minimum distance from the curve y equals 2x squared. So we've got y equals 2x squared. Okay, to the point 0, correct to 2 decimal places. So what we're going to do is we're going to draw a little graph here, okay, which are given us in the book to give us a hand. Okay, so we've got the quadratic y equals 2x squared. Okay, and we want to come across here. It's going to be at 4, 0. Okay, and we want the minimum distance here. Okay, and that's going to occur when they're at right angles. Okay, they're going to occur when they're at right angles. Okay, so what we're going to do is we're going to have a look at our distance formula. Okay, so our distance formula is basically Pythagoras' theorem. Okay, it's x2 minus x1 squared plus y2 minus y1 squared under our square root sign. Okay, so for this, we're saying that we've got our x minus 4, because we know our 4, okay, plus y minus 0, because we know it was at 4, 0. Okay, which means we've got a distance formula of x take 4 squared plus y squared. Okay, is our distance formula. Okay, and what we need to do though is we know though that y is equal to 2x squared. Okay, so we can get rid of our y in here and say that we've got x take 4 squared plus 2x squared squared. Okay, so we can write that as x take 4 squared plus 4x to the 4 to the power of a half. Okay, if we expand out these brackets here, okay, it means that we're going to get x squared take 8x plus 16 plus 4x to the 4 to the power of a half. Okay, so we've got a function now, okay, for our distance. Okay, so we've got a function for our distance where we start off with a function for our distance that had x and y's. Now we've got a function for our distance that's only in terms of x. So we've got to minimise this distance, and we've got to find the derivative of it first. So remember, our quick way of the chain rule is our half comes down the front, okay, times by the derivative of what's in the brackets, which is going to be 2x minus 8, 16 is going to drop out, okay, plus 16x cubed, okay, times by our original part that we had, okay, which is our x squared take 8x plus 16 plus 4x to the 4, and that will now be to the power of negative a half, because we're going to take one away. Okay, it doesn't look very nice. Okay, and fix it up a bit at least, and say that we've got our, just change this in our better order and make it 16x cubed plus 2x minus 8 over 2 times square root, okay, of our 4x to the 4 plus x squared minus 8x plus our 16. Okay, and we can cancel out our 2 here as well, make it a little bit nicer again, and say we've got 8x cubed plus x minus 4 over our square root of our 4x to the 4 plus x squared, take 8x plus 16. Okay, and we're going to make that equal to 0. Okay, so you think, oh, geez, that's going to be horrible, but don't forget we can just multiply our entire line across, so which means it's all going to disappear, and we can just say we've got 8x cubed plus x take 4. Okay, it makes it a fair bit nicer for us at least. Okay, when we solve that, okay, which we can just do with our CAS calculator at this point, we can say that x is equal to 0.741. Okay, so clearly if we'd been going about this and trying to find factors, it wouldn't have worked very well, so we could just use our calculator. Okay, so we know then that our minimum distance occurs, okay, at this value of x. We need to put that back into our distance formula that we had. Okay, we can just use this one. The distance of 0.741 equals the square root of our 0.741 minus 4 squared plus 2 times 0.741 squared. Okay, and that's going to give us 3.439. Sorry, the minimum distance is 3.439 units. Okay, so just to recap what our process is. Okay, so we need to define a function. Okay, we often need to do some work with that function to eliminate a variable that we don't want, and all that stuff can be a little bit of hard work. Okay, so we're down to just one function with one variable in it, like we had here. Okay, you then go take the derivative of that variable, okay, set it equal to 0 and solve for that variable. That's going to tell you the point where you're at a minimum. Okay, it's not the minimum value, okay, it's just going to be the point where it's the minimum. You then sub that value back in to your original one that you found, okay, to get the actual one, okay, to get your minimum, maximum, whatever. Okay, again, we have to find the minimum. We only got one answer, so we don't have to worry too much about checking to see if it is or not. Okay, so hopefully that's enough to get you through on this section.